to talk about net radiation, specifically the 4 components, and then selection among sensors. Bruce will talk a bit about radiation frost and non-destructive measurements of leaf chlorophyll, and then I'll talk about hyperspectral reflectance. And if we get that far, and if people are interested, we can speak a bit about soil oxygen and barometric pressure, but we'll just see where we're at after we get to the end of the reflectance stuff.
I think we'll get to it.
Okay.
We'll see.
Yeah, as long as interest is still there, people's eyes are open at that point. All right, so as before, if you have any questions, please feel free to ask. I don't have that many slides this time. I might make use of the board. And a lot of what we've covered already when we talked about pyranometers and infrared radiometers relates directly to net radiometers, the instruments that we use to measure net radiation. And so we won't talk maybe as much about principles of sensors in the net radiation section. So net radiation is just the difference between incoming radiation at the surface and outgoing radiation at the surface. And there are both shortwave and longwave components that we have to consider. So I passed out a magnet. If you don't have one, there's more down here, and you're free to take one that has the exact same picture that you see right here. But these are typical values of the 4 different components that make up net radiation. This would be representative of a clear summer day over vegetation near solar noon, so when the sun is in the middle of the sky. So the largest component of net radiation is the incoming shortwave component. 100 watts per meter squared is a reasonable value for midday in the summertime. Then the vegetation or soil, whatever is at the surface in the summertime, usually it's vegetation, is a good absorber of shortwave radiation. So a much smaller amount is being reflected. About 200 watts per meter squared is a good estimate for vegetation. So the difference between these two, the incoming shortwave minus the outgoing shortwave, is net shortwave. And so we have a positive value of 800 watts per meter squared net shortwave at the surface. So a term that you're probably all familiar with is albedo. That's the broadband shortwave reflectivity. And so essentially it's just the ratio of these two numbers. In our example, it would be 200 divided by 1,000, so it's the reflected shortwave divided by the incoming shortwave. That would be 0.2 or 20%. That's a really reasonable value for green vegetation when the sun is in the middle of the sky. So now we switch over to the long wave slide. We also have an incoming long wave component and an emitted long wave component. So if the sky is cloud free, and a lot of you were just outside with me pointing infrared sensors up and measuring, the sky was quite cold, but we found that the clouds were a bit warmer than the blue sky, right? So the sky is emitting long wave radiation towards the surface, and the surface is emitting long wave radiation back towards the sky. But the reason the incoming radiation from the sky is lower than the emitted radiation from the surface is the sky is colder than the ground surface. At least it typically always is in the summertime, especially if the sky is clear. If it's cloudy, they can be pretty close, and these numbers can be a lot closer. So if we were to actually take the measurements that we were making outside, I think a lot of us were seeing like -20, -30 Celsius for the sky temperature that we were measuring with those infrared sensors. And we put that temperature in the Stefan-Boltzmann equation. And let me just write that over here on the board. It was in an earlier slide, but just to remind everyone. this way. So energy is equal to a constant that we use as sigma times the absolute temperature raised to the 4th power. So if we were to take one of our measurements outside, we'll just say the blue sky was negative 30 Celsius, and we were to plug it into this equation, we would get a number that's a lot lower than 300 watts per meter squared. The reason why is those infrared radiometers we were using outside, they're only measuring the wavelengths between 8 and 14 micron. You remember from the infrared presentation that I gave this morning, when we're trying to measure temperature, we have to have sensors that have a filter over them that only gives us 8 to 14 micron, because that's the atmospheric window where the sensor can effectively see through the atmosphere to the surface that we're trying to measure the temperature of. So when we're trying to measure net radiation, we don't want the 8 to 14 micron filter on our long wave radiation sensors, because we're trying to measure all of the radiation coming from either the atmosphere or the land surface. We're not that interested in the temperature, in other words, and we don't want to see through the atmosphere and measure the cold temperature. We want to actually capture the radiation coming from the air molecules and the clouds and everything that's in the air. And so long wave sensors don't have an 8 to 14 micron sensor on them like the infrared temperature sensor does. And that's why if we were to plug in negative 30 Celsius here, we wouldn't get 300 watts per meter squared. I can't remember what negative 30 Celsius is when we plug it into the Stefan-Boltzmann equation, but it's a lot closer to like 150 or 200 watts per meter squared. But that being said, the sky, when we're talking about all of the long wave wavelengths, the sky is still colder than the ground surface, and so there's less long wave coming in from the sky than what's being emitted from the surface. And in this example, the net long wave radiation is negative 150 watts per meter squared. And so net radiation then is just the sum of these two numbers. Net shortwave plus net long wave gives us net radiation. It's 650 watts per meter squared. And essentially, that's what our equation here says. The symbol we use for shortwave is shortwave SW, and then subscript I for incoming, subscript O for outgoing. Symbol for long wave is LW, same subscripts. So any ideas of what these values will look like for the winter over snow? Everybody has the magnet, but don't cheat. Say it loud. Exactly right. So you're going to get a lot greater reflectance here because it's snow on the surface instead of vegetation. The albedo of snow is often around 0.7 or 0.8 if the snow is kind of old and dirty, or like 0.8 to even 0.9 if the snow is fresh. It's really reflective. So how does this one change? So we know there's going to be greater reflected radiation, but how does this one change in the winter?
400.
What's that?
400.
Yeah, but you're cheating. You've got the magnet.
Just you were reading.
Oh, no, I'm kidding. I'm kidding. It's okay. So we all know that the seasons change, right? And the reason the seasons change is because the sun angles get much lower in the winter versus summer. And so this number gets a lot lower just because the sun is at a much lower angle. It's winter, right? So if this guy is lower, we have less overall shortwave coming in, but we have a much larger reflected component because we have snow on the surface. What about these two? How do they change in wintertime? So remember, these ones are dependent on temperatures. Yeah, exactly. It's colder in the winter than it is in the summer. So the sky gets a little bit colder and this number gets smaller, but not a lot. But the surface actually gets a lot colder, and so this number gets quite a bit smaller. And so now if we look at, and everybody has the magnet, reasonable values for the middle of the winter, in the middle of the day, over a snow-covered surface. Incoming shortwave is only about 40% of what it is in the summer, 400 watts per meter squared. The reflected component is a lot bigger, so because the snow has a high albedo. Somebody that can do math in their head, what's 350 divided by 400? That's about 0.85 roughly, I think. Yeah, 0.875, right. So the albedo in this example is almost 90%. That's a high reflectivity. And then you can see the incoming long wave from the sky does go down a little bit, but not as much as the outgoing long wave from the surface. So essentially in the wintertime, the sky temperature and the surface temperature are closer to the same value, and they're both cold. And so our net short wave here is positive 50. Our net long wave there is negative 50, and so the net radiation is actually 0 in this example. And so this is true of the middle of the winter. What about at night? What happens? Yeah, I mean essentially the yellow arrows and the yellow numbers go away, and we only have long wave at night. And so if we only have long wave at night, that means net radiation is a negative number at night, and that's why it cools off a lot at night. The surface is now losing energy to the atmosphere rather than gaining energy as in the day. Okay. So the reason that we are interested in measuring net radiation is it's a major driver of surface processes. I kind of have just explained one, heating and cooling, but another one is evapotranspiration. So in many cases, net radiation is the biggest driver or the biggest contributor to evapotranspiration. Vapor pressure deficit, which Bruce talked about a lot this morning, is another one of the major drivers of evapotranspiration. So there's lots of reasons that net radiation could be applicable, especially in environmental and ecological studies. And so here's a slide showing the surface energy balance. And here's a simple surface energy balance equation. Net radiation is a major component. And so we won't consider the radiation terms in too much detail. They were on the previous slide, but you've got incoming shortwave streams, and then the outgoing, the reflected shortwave streams. Then long wave radiation coming from clouds and sky. Whatever's in the sky that has a temperature is going to be emitting long wave radiation towards the surface. And then plants and soil, whatever's at the surface, is going to be emitting radiation back towards the sky. Right. The G term is the soil heat flux, so the flux of energy into the ground. The H term is the sensible heat flux, the heat gain or loss due to conduction and convection. It usually is heat loss during the day because often the surface is warmer than the air, but not always. The surface can be colder than the air, so there can be a sensible heat flux towards the surface. And then the LE term is the latent heat loss, which is the combination of evaporation and transpiration. And so there are other terms like photosynthesis would be a small contributor, and there can be heat storage in the plants themselves. Typically heat storage doesn't happen in crops, but can in forests. So we just defined those, but here's the real point. The available energy, and we call the difference between net radiation and soil heat flux as available energy, because that's everything that's available to do things like evaporate water or heat the surface, for example. We often find when we make measurements of all of these terms, like at eddy covariance sites, for example, when we can measure sensible heat flux and latent heat flux with gas analyzers and sonic anemometers, we often find that the available energy is not balanced by the heat fluxes at many measurement sites, right? And it should be, the energy coming in should equal the energy going out. So the real point is net radiation measurements have to be accurate for surface energy balance studies. So I'll talk a bit about net radiometers, and I'll also talk a little bit about net radiation modeling, because earlier we were talking many routine weather stations that we have in like weather networks. They're going to have a pyranometer on there to measure the incoming shortwave radiation, but a lot of times they don't have any other radiometers. When we were talking about photosynthetic radiation earlier, weather stations typically don't have PAR sensors on them to measure the photosynthetically active radiation, and they often don't have a net radiometer on there to measure net radiation. And so you can model net radiation from incoming shortwave radiation, and I'll talk about that in addition to measurements of net radiation with net radiometers. So there are 4 kinds of net radiometers, and I'll start with the most complex, and then I'll move to the simplest. And most of the time, you don't see too many of the intermediate types of net radiometers. Usually there's 4 component instruments, which are the most complex, and they're quite common, or there's single component instruments, which are the simplest, and they're quite common. A 4 component net radiometer has an individual sensor for measuring the 4 components that we just described. So you've got an upward looking pyranometer that measures the incoming shortwave. You've got a downward looking pyranometer that measures the reflected shortwave. You've got an upward looking PerG Ometer that measures the incoming long wave. And you've got a downward looking PerG Ometer that measures the emitted long wave. And so pyranometer is the name of the sensor for shortwave radiation measurements. PerG Ometer, kind of a funny word, is the name of the sensor for measuring the long wave radiation. And so they're very similar instruments. Both of them consist of a thermopile detector, and Bruce talked about thermopiles, pyranometers earlier today. Essentially it's a device that measures the heat difference across the bottom surface and the top surface, or the top surface and the bottom surface of the plate. And then over top of the thermopile, there's a black body absorber. So the black body is just used to absorb all of the incident radiation on it. Then pyranometers have a glass dome over top of the thermopile and black body detector. The reason for the glass dome is twofold. One is to give it accurate cosine or angular response, and the other is to block all of the long wave radiation. So for a pyranometer, we're only interested in the short wave wavelengths. The glass is only transmissive to short wave radiation. So we have to put a glass dome over top of the black body so that it blocks the long wave, lets the short wave through. Therefore, the black body will only absorb the short wave, and the thermopile will only measure the short wave radiation. So the downward looking pyranometer is the same thing, it's just inverted. It's one of them that's mounted upside down. The PerG Ometer is very similar. The only difference is instead of having a glass dome, it has a silicon dome over top of the black body. And I know what I've drawn here doesn't look like a dome shape. Sometimes the PerG Ometers will have a small dome shape, other times it'll just be a flat surface, so it's actually a silicon window rather than a dome. And so the reason that we use a silicon dome is because it blocks the short wave radiation and transmits the long wave radiation. So a PerG Ometer is designed to measure long wave. We have to block the short wave and allow only the long wave through so that the black body absorber can absorb it and the thermopile can measure it. And so here again you've got one up, one down to measure the short and long wave. Some examples of this type of net radiometer are the Hawkesbury, that's a Dutch company, and Kippenzonen, also a Dutch company. They both build 4-component instruments that work very well, and I'll show you some pictures in a minute. Apogee Instruments also builds one. I don't really have a good demo to show you, but I will pass this around so you can see what an instrument actually looks like. So this sensor here with the white diffuser on the top is the upward-looking pyranometer. I know I just said they typically have glass domes. This one doesn't have a glass dome. It has an acrylic diffuser, which is also transmissive to the shortwave wavelengths. The bottom pyranometer is a glass window. That's this one. Then the two PerG Ometers have black, flat black windows that are made of silicon. They look the same, up and down. So you're welcome to have a look. Yes?
Price of these, the range of price for these.
For these ones, the Hawkesbury is probably, these numbers are going to be in US dollars, so I don't know what they would be in Australian dollars. And you'll have
There's the equivalent one made in Australia. It's about $6,000 or $7,000.
Okay, so yeah, that's correct. Middleton builds one.
Yeah, and I can tell you the designs of these things haven't changed since I did my PhD. You have a plastic thing there, and you've got to pass air through it, and the whole bit to keep the dome up, keep the condensation out of it. This is the first one. I know this is not a promotion that I did in an Apogee workshop though. This is the first one since I did my PhD that I've ever seen that become a realistic price that will actually work in the field without you having to almost sit beside it.
What's the price of the Apogee one?
I don't know.
That one's
haven't been officially released.
Yeah, I will.
Sorry.
I guess I can say the price. Peter's the one who sells it in Australia, but the US list price is about $2,500. Right. What's that?
Australians do it at 1 1/3.
You're right, but it will. You also have to pay for importation and all that stuff. So. This Kippen zoning unit is about $6,000, I think, maybe a little higher, because it comes with a heater and ventilator on it. The Hawkesbury unit is closer to $5,000. I think it's between $4,500 and $5,000 US dollars. So that gives you an idea of the price tag of these sensors. And in a minute, I will compare in a relative sense, I'll compare the price of all of the above, because we're going to put 3 more pictures like this one on the slide here. So the next type is a net all-wave radiometer, and this one is the simplest version. You basically have one thermal pile, and it's sandwiched between 2 black body absorbers, one on top and one on bottom, and then there's 2 polyethylene domes over top of the absorbers. And so what you have is a thermal pile that's just outputting a signal that's proportional to the temperature difference between the top surface and the bottom surface. And that temperature difference between the top surface and the bottom surface is dependent on the radiation incident on the top and the radiation incident on the bottom. The reason this is called a net all-wave radiometer is that it's measuring each surface, the upward-looking surface and the downward-looking surface, are measuring all of the wavelengths at the same time. So it's sensitive to shortwave and longwave together. Polyethylene actually transmits shortwave and longwave. And the reason for the polyethylene domes is just to basically be a weather barrier and keep rain and moisture and dust and dirt off of the black body surface. Not all of these net all-wave radiometers have polyethylene domes. So there's probably the most common one, at least historically, is this Rebs. Rebs stands for Radiation and Energy Balance Systems, model Q star 7.1. That's an American-made instrument from the state of Washington, and they were used a lot, especially in past decades. Now it seems like the Kippen Zone and NR Light 2 is the most common type of these net all-wave radiometers. The Rebs has the polyethylene domes, The Kippenzonen NR Lite 2 does not. So the real challenge of polyethylene domes is they're flimsy, and they're you have to keep them pressurized often in order for them to not collapse. At the same time, polyethylene is better at transmitting shortwave than it is at transmitting long wave. And so when you get different proportions of long wave and shortwave, say clear sky versus cloudy sky, for example, or over vegetation versus over snow, it can really influence the accuracy. So the polyethylene domes, while they can keep it clean and free of water, they also have their challenges. They have to be replaced quite often because they're flimsy. Birds like to peck holes in them. So the Kippenzonen NR Lite, in doing away with the polyethylene domes, they get around at least part of the problem of the domes, but at the same time, when the surfaces get wet, the radiation balance goes way out of whack and they don't yield accurate measurements until they're dry. So these ones, while they're the simplest and the cheapest, also are the most prone to errors. We just talked about prices for all of these. These guys are probably $1,500 to $2,000 US, somewhere in that range. Okay, I won't spend nearly as much time on these two intermediate types, just because this is the only example of this type of two-component instrument that I'm aware of, and it's no longer available. So essentially it works a lot like this one, where you have a single thermopile that's measuring the net difference between what's coming in and what's coming out. It's just that we separate shortwave and long wave. So we actually have two components. One of them is measuring net shortwave, the other one's measuring net long wave. This was a nice instrument when it was available, but it didn't last very long on the market. The other type is also kind of like that one, but rather than being a net device that only gives you one signal that's proportional to the difference between all of the incoming radiation and all of the outgoing radiation, is that they separate the pirateometers. So you've got two of them. You've got an upward looking one that's sensitive to both the incoming shortwave and the incoming long wave, and then a downward looking one that's sensitive to both the outgoing shortwave and the outgoing long wave. Right, so a good example of this one is the Philip Schenk model 8111. It's a European instrument. I believe it comes from Germany, maybe Switzerland. I can't remember for sure. But this one is not a very widely used instrument. Predominantly you'll see this or that one. So I said I had some pictures. Here's what they all look like. The Huxaflux and the Kip, and then the Apogee that I passed around the room is in the middle. So the major advantages of a 4-component net radiometer is that you get an individual measurement of each one of the 4 components. And that's a major advantage because typically that gives you higher accuracy. I say potentially here because 4 individual sensors also means you've got 4 components that might cause problems. Like if one of them isn't calibrated correctly, that can be a problem. Or you've got 4 of them that might get dirty, for example. And then we already talked about price. These tend to be higher cost. So just one design feature that I will mention with regards to the Apogee is that it has an SDI-12 output. And so we get around this need for all of those data logger channels. What this means is in this center box here on the Apogee unit, there's a circuit board in there all the outputs from the individual radiometers are being measured by the analog to digital converter on that internal circuit board. And then we're just digitizing those signals and outputting an SDI-12 measurement so that you can plug it into one single digital channel on your data logger and not have to tie up all of the analog channels to make the measurement. So now if we look at the net all-wave radiometers, here's the two examples that I listed in the previous slide. There's the polyethylene domes, and that one's the domeless model. So again, these domes, they're better at transmitting shortwave than they are long wave, which can lead to errors. They don't always stay inflated. If they get a hole in them, they'll get water condensing on the inside. It can cause big problems. The domes need to be replaced periodically. This one, because they're domeless, they're exposed to the environment. They can get wet and dirty, and that can lead to aeration. But the main advantages here are it only requires one data logger channel to make the measurement. Remember, it's a single detector where the signal that it's outputting is proportional to the difference between everything that's coming in and everything that's going out. So that only requires one analog measurement. These do tend to be smaller and lighter weight, so they can be easier to mount and keep level. And we already talked about price. They tend to be lower cost. But the major disadvantages, they have fragile domes and they're domeless. This domeless guy requires a wind speed correction because if the wind's blowing over top of it, it can change the energy balance. If you have mismatched detectors, that can be a big problem. Essentially what that means is you only have a single sensor and you've got one detector surface on the top side of that sensor or thermal pile and one detector surface on the bottom side of that thermal pile. They have to have the same sensitivity to shortwave and longwave, and they have to have the same sensitivity to each other. Otherwise, they're only accurate for the conditions that they're calibrated to. And if the conditions are changing like they do in a dynamic environment, then the mismatched detectors, so the upward sensitivity doesn't match the downward sensitivity, can lead to errors. They tend to be higher maintenance. For example, you have to replace the domes, and all of the above combined lead to lower accuracy. So this is just a summary slide, and I'll mention that a few years ago, before Apogee started building net radiometers, we were interested in potentially selling net radiometers from other companies. And we did an extensive field study where we compared several different models of net radiometers for part of the growing season over a uniform turf grass field in Logan, Utah. And so the citation to our work is here. If you're interested in getting the paper, again, shoot me an email and I will send you a PDF. But the major findings are that the 4-component net radiometers did indeed provide the most accurate measurements. But I put an if in here. You have to make sure that the radiometer is level, and you want to make sure that the individual sensors are clean. The net all-wave radiometers were the simplest, but they did have lower accuracy, and it was due to lower sensitivity to long-wave radiation. The last line I think is important. We found that net radiometers were capable of measuring net radiation with better accuracy than what's often reported in the literature. There's quite a few studies out there, like energy balance studies, especially at flux tower sites, that indicate net radiation uncertainty is like 10 or 20%. I think if you're measuring it with a 4-component net radiometer that's well leveled and clean, then the uncertainty is probably lower than what's usually reported in the literature for net radiation measurements. Any questions about measuring net radiation? So I'll just take a minute on, I don't have any slides for this, but I think I can make use of the board. I might not even need to make use of the board. I think I can just explain it. And for those of you that are interested in modeling net radiation, again, we can talk afterwards, or you can send me a follow-up email and I can give you more detail. But for those cases when you have weather data and you need net radiation, but the weather data did not include a net radiometer to measure the net radiation, you can model it. The most important component that you need is a measurement of the incoming shortwave radiation from a pyranometer. If you're looking at your fridge magnet, or if you remember my first slide, usually the largest component of net radiation is the incoming shortwave component from the sun. So if you have that measurement, you have at least a reasonable idea of net radiation, and you can model the other components. Typically how it's done is then to take a published value of albedo for the surface that you're measuring. So if it's vegetation, it's going to be pretty low, around 0.2 to maybe 0.25. If it's snow, it's going to be quite a bit higher. Published values of albedo are fairly accurate if the surface conditions don't change dramatically. So if you're trying to do this when the vegetation's always green, just estimating or taking a published value of the albedo and calculating the reflected shortwave component that way works pretty well. The challenge is if you're trying to do this over the course of, say, a whole year, when you might have, snow or bare soil in the winter time, and then the crops start to come up, and you have green vegetation and soil mixture, and then the crops fill in and you only have green vegetation for the most of the growing season, and then the crops senesce and they turn yellow, and then you harvest them. I mean, the surface can be quite dynamic over the course of a whole year, so you can only use values of albedo if you know what it is for the surface or have a good estimate of it, and if it's not changing significantly. If the surface is changing a lot, then you have to change the albedo in your model. So the way that Longwave is often estimated is from measurements of air temperature and relative humidity. And then we can predict Longwave pretty well from equations like this. So this is the Stefan-Boltzmann equation, and emitted energy is proportional to a constant times the fourth power of temperature. So if we know reasonably well what the fourth power of temperature is for the surface, then we can estimate Longwave relatively well, the component that's being emitted, because we know that most surfaces are black bodies. Most land surfaces are black bodies. So if we're working with plant canopies or soil or snow, the emissivity right there in the equation, this number is going to be close to 1. So if we have a reasonable estimate of the surface temperature, we can estimate the emitted Longwave component, so the part that's going from the ground to the atmosphere, from this equation. To estimate the incoming Longwave component, we use the exact same equation, and oftentimes we use the air temperature as a proxy for the sky temperature. The challenge with doing incoming Longwave radiation estimates is this number is the hard one, and you were asking about that earlier. So there's ways to estimate the emissivity for the atmosphere, and that's where the humidity measurement comes in. It's usually empirical equations that estimate atmospheric emissivity based on sometimes air temperature, but typically the vapor pressure of the atmosphere. And the error can be kind of high because atmospheric emissivity is not always that dependent on the vapor pressure near the surface, right? The vapor pressure that we measure at the surface typically comes from a relative humidity probe that might be 2 meters off the ground, but the Longwave radiation coming from the sky is coming from the whole depth of atmosphere, from 2 meters above the ground till way up in the atmosphere. And so if the near surface vapor pressure is reasonable estimate of the whole column of water in the atmosphere, Then empirically, estimating atmospheric emissivity from near-surface vapor pressure works okay. If the near-surface vapor pressure is not a good estimator of the whole column of water in the atmosphere, then the empirical equations don't work that well. So there are ways to model net radiation if it's not available, but I would recommend measuring it if you have the equipment to do so. And if you're interested in learning more about how to model net radiation, please send me an email. I can help with that. There's quite a bit of information in the literature that's been published. There's a really good study from about 2007, I think, maybe 2009, where some folks at USDA in the United States compared a whole bunch of different incoming long-wave radiation models and assessed the accuracy relative to measurements. Any questions? I believe that's all I have for net radiation. So.